Hello everyone, welcome to Science Prodigy. Today we will be continuing the questions on equations of uniformly accelerated motion, or you can call it motion in one dimension. In the last video I had completed till the part of free fall. So today I'll be continuing with certain important questions on free fall as well as the remaining part of the topic. As you can see, I have already noted down one question which says that draw a diagram to illustrate the motion of a body whose speed remains constant but the velocity continuously changes. So the given thing is the speed will remain constant but the velocity continuously changes. This means that the direction is changing, speed remaining constant, and that is only possible in case of a uniform circular motion. The speed will remain constant but the direction at every point of the circular motion will keep on varying. So the diagram will be that of a circular motion. A particle constituting circular motion will be having the same speed but different velocity because of the change in direction. Okay, so now we will be moving towards the next question. Okay, so now as you can see in the second question, a particle is thrown upwards with an initial velocity u. Find the time taken to reach the highest point of its path. So it is a general question, means a generalized sort of a question. You can solve this question using different numerical data, but let us analyze this in the general manner. We have been asked to find the height of the particle. So now if I actually see, it is actually moving upwards with an initial velocity. So if I actually apply v is equals to it is not asked to find the height, it has been asked to find the time. So if I use v is equals to u minus gt. Why minus gt? Because it is going upwards, so there is negative acceleration acting on it. Final velocity at the highest point of its path will obviously be 0, because at the highest point, when it reaches the highest point, it has to stop. So v is 0, u has been given as u minus gt. So the time taken to reach the highest point will obviously be equal to u by g. Okay. So always the time taken to reach the highest point of the path is nothing but u by g. Okay. In this question, it has been given that a particle is thrown upwards with an initial velocity u. Find the maximum height to which it rises. So now when it goes to the maximum height, as I said in the previous question also, the maximum height means the final velocity becomes 0, and because it is moving upwards, it is against the acceleration due to gravity. So we will be taking acceleration as minus g here. So I can easily apply v square is equals to u square minus, because it is moving upwards opposite to direction of acceleration, I can easily use this where s will be the maximum height. Now v becomes 0 at the maximum height, and u square minus 2gs, 2gh, because I am talking about height, it is better to mention height as h. So I can easily say that the maximum height is nothing but u square by 2g. So this is a very generalized answer. Whenever you are asked find the maximum height with this sort of data, you can directly apply by showing that it is coming from this one, that the maximum height reached is nothing but u square by 2g. Okay. In this question, it has been given that a particle is thrown upwards with a velocity u. find the velocity when it comes back to the point of projection. It is like a theoretical question. It is only for the understanding that what happens when it comes back to the point where it was projected. The moment it returns back to the same point, it will have the same velocity of the same, not same velocity, but the velocity having the same magnitude u. So the answer is that when it comes back to the point of projection, the velocity magnitude will remain the same. That is, the velocity magnitude will obviously be u meter per second, but as because in the first case it was projected upwards, when it returns back it will be actually pointing vertically downwards. So velocity magnitude wise is the same, but the direction is now anti-parallel. The direction is now reversed. It is acting vertically downwards. Okay, so this is a very important point to be. Has been given that a stone dropped from the top of a tower reaches the ground in 4 seconds. Find the velocity when it just reaches the ground. Also find the height of the tower. So first of all, it has been given that the stone is dropped. That means u is equals to 0. Then the time is given as 4 seconds. So v is nothing but u plus gt. If I directly do, the value becomes 40 meter per second. For the next part of the question, also find the height of the tower. I can directly evaluate h is equals to ut plus half gt square. Ut part will become 0 because u is equals to 0. Half gt square, if I directly apply, the value comes out to be, I will consider taking g as 10 instead of taking g as 9.8. I will round it off and take it to 10 upon my discretion. So the value comes out to be 80 meters. Now if I begin with the graphical analysis of motion, where we will be studying motion in the form of different graphs. Okay, so beginning with the position time graph. So if I start with the plotting of the position time graph, I will notice that if I say, suppose I am plotting x on the y axis and time obviously on the x axis, and if I show this position time graph in this format, that it is a straight line parallel to the x axis and passing through 0, 5. What does this mean? What does this position time graph show me? From the position time graph, I can actually infer that it is actually remaining in the position 0, 5. Okay, that means it is remaining in the position of that particular 0, 5 and it is at rest in that position. Why at rest in that position? Because the position is not changing, it is constantly 5. So it is actually remaining in that position, and with as time passes the position is also remaining constant. Its position is not at all varying. But now if I actually vary this, if I actually plot the graph in this way, that means its position is constantly varying, but the only thing is this sort of a straight line graph represents a uniform motion. That means it's actually covering equal distances in equal intervals of time. Equal distance in equal time interval means it is moving with a constant velocity. So these sort of straight line graphs passing through origin, that is this sort of position time graphs, actually imply such that when there is a equal distances covered in equal intervals of time, they imply that there is a constant velocity. The velocity is not changing at all. Okay, so it is constantly moving because it is upward. I can say that this is moving towards, suppose, the positive side, that is towards the right hand side. But now if I actually go for this sort of a graph, we can see that this graph is also representing a velocity only, but this will be only possible when the object or the body is actually moving towards the left hand side, and as a result of that the velocity part, the x part is becoming negative. Okay. So similarly, if I plot the velocity time graph, if I have to show that yes, this is a constant velocity, suppose. So, draw the velocity time graph to show that it is a constant velocity. So, the moment I go for plotting a Vt graph, you have to mention the units, that t in seconds, v in meter per second, or whatever is given. If I am asked to draw the graph of uniform velocity, that means the velocity will remain constant. So, suppose the velocity is given constant and it is 10 meter per second. So, I will be drawing a straight line parallel to the x-axis. That means this velocity 10 meter per second is remaining constant over all the time intervals of x. So, this graph, this Vt graph gives me a constant velocity of 10 meter per second, which is constant with respect to the passing of time. But if it is a uniform velocity, if it is asked to plot a uniform velocity, then again it will be of this type, that is the velocity is increasing but in a uniform fashion. Same goes for decreasing in a uniform fashion, and the slope of this particular graph, if I see this point as v and this point as u, so del v del t, which is the slope of this particular graph, this slope is given me the acceleration. So, the slope of the Vt graph can give me the acceleration. So, slope is nothing but y2 minus y1 by x2 minus x1. So, this y2 value, final value, minus initial value, if I am plotting, suppose this value is u, so v minus u. Now, x2 value is, suppose this time period is t2, and x1 value is nothing but t1. So, this slope calculation y2 minus y1 by x2 minus x1 is v minus u by t2 minus t1, that is, this is nothing but delta v by delta t, and we know that del v del t is nothing but acceleration. So, we came to know that the slope of the Vt graph provides us with acceleration. So, the moment we do del v del t, we can easily obtain acceleration from the slope of the Vt graph. We can also obtain the distance travelled from a Vt graph. How? If we go for the area of the Vt graph. Why the area of the Vt graph gives the distance travelled? Area of the Vt graph, suppose area enclosed by this part, that is the area of this part. If I find the area of this particular triangle, I can easily find that it is half into, in case of the base of this triangle is T2, I am considering the bigger triangle area, and the height of the triangle is nothing but V. So, on computing this area, this is nothing but the distance covered, because it is a Vt relation. So, the moment we go for the distance calculations, it is nothing but V into T. That is why whenever we compute the area of the velocity time graph, that will obviously yield me with the distance. So, it will always be the area between the curve and the x-axis or the time axis. So, the area based on the figure, if it is a triangle, you will be going for the formula for triangle. If it is a trapezium, rectangle, accordingly the area of the graph with this enclosed, you will go for that, and that area is nothing but in the form of V into T. That means the area of the velocity time graph gives me the distance. So, two important points, area gives me distance and slope gives me the acceleration from the Vt graph. So, with this we end today's video. So thanks for watching. Keep watching. Thanks a lot.